Welcome back to Retro Depot. Today is the first time that I've uploaded a video in a while, and there's been several reasons for that. A lot of it has to do with life. It's been a busy year, a lot of chaotic stuff going on. The pandemic, work, just trying to get things done here at the house. Everything that you can think of has caused me to not really have a whole lot of time for uploading videos or working on projects. Now, that said, I have been thinking about doing this video for a little while, and this is hopefully going to be part of a larger series of videos. But the premise behind this is essentially working on building a somewhat universal ASIC for a Z80 based computer, and today we're specifically going to be talking about a memory mapper, a memory management unit. And the idea being is that with a lot of Z80 computers, because they only have an address space of 64 kilobytes, there's just not a lot of room for being able to run things as program wise, or they're fairly limited in many aspects. So that said, I've got several things that I've been planning on doing as far as this is concerned, and I wanted to do a video about designing a memory management unit. Now, there's several things that we need to take into consideration. First is obviously the limitations of the Z80, and that's primarily that it does only have a 64 kilobyte address size, a 16-bit address. Now, another thing that we have to think about is how big of a memory area do we actually want. Now, I did another little project here a little while back, and I posted it on my website. But it expanded the ability of the Z80 to address up to 4 megabytes of RAM and 4 megabytes of ROM. But that's a little bit overkill for most projects. So with this, we're going to be looking at trying to stay in a 512 kilobyte address for both RAM and ROM. And with that, we're wanting to make sure that we can address these in windows. And what I mean by windows is we're going to divide the memory range up into a series of windows that we can then bank various different pages into. Now, that brings me to page size. Now, a lot of guys will do something along the area of 8 kilobyte page size, but really that's a bit overkill for a lot of people. It's very complex to program for. You have to keep track of a lot more stuff. So I've elected to aim for 16 kilobyte window size, which will give me 4 windows of 16 kilobytes for a total of 64 kilobytes. And within each window, we can bank in a page of either ROM or RAM. And then the final consideration that we have to take into mind is construction. Now, in this particular project, I am planning on designing this for a CPLD. Now, you could easily do this for something along the lines of an FPGA, or even constructing it from, discrete logic. But with that said, it really comes down to how much real estate are you going to actually give up. Discrete logic is going to take up a bunch of space. Now, CPLD or FPGA, it's not quite as bad. The particular FPGA that I'm going to be looking at using is the Max 7000 series CPLD, because it is 5-volt compatible, and that will give me the ability to have 128 macro cells. Now, that said, the next thing that we need to think about is how does a memory mapper work? And probably the most common way of using one is through the use of registers. You'll have page registers, so to speak. So in a situation like this, since we are aiming at having 4 windows, we need to have a page register for each window. Now, if you don't understand how registers work, don't worry, I'm going to go over that here in just a moment, but we then have to take those page registers and actually incorporate it into a system that when we access that page, that the correct value is written onto the address bus. So sit back, enjoy the video, and if you have any questions, feel free to post them below. I am going to give you a heads up that this is going to be a longer video, so you might even get yourself a drink or a snack and sit back and take notes. Alright, so let's get started. So when we talk about a register, essentially what we are talking about is a series of flip-flops that can store data. That's the easiest way to think about a register. And of course we have to be able to not only write information to that register, but we also have to be able to read that information from that register, or at least it's preferred that we be able to access that information for reference. Now, a good example of a 8-bit register is the 74574, and what this is it's an octal flip-flop. You have 8 inputs, 8 outputs. You have a clock and an output enable. Now, if we actually look at how this is constructed, and of course I'm using a program called Digital. I will leave a link below so that you can download this software if you choose to. But I'm using this because it's great for both simulation, construction, by schematic, and then also you can export to either VHDL or Verilog. So that's the purpose of why I'm using this particular program. But if we take a look at the 74574, and we can do that by opening the circuit, and let me resize this a little bit and get it here in the middle of the screen. This is the basic construction that you will see within Digital. Now, this isn't a true construction for this register. Essentially, the way you would have this done, and you'll have to know a little bit about this program and building circuits digitally, through a simulator. But each one of these data lines comes in, and this is essentially a multiplexer here. And then the way you can read this is that this flip-flop has 8 inputs and 8 outputs. Okay, and then it's got a common clock, and once those outputs come out, they are tri-stated on a buffer. The output enables this to either display or not display the data from the individual ports. So if we think about it, it's just 8 flip-flops on the inside that have a common clock. Their outputs are buffered by a tri-state buffer, and data goes in, you clock it to latch the data, and then you have to bring the output enable low in order to display that data. Okay, so it's pretty straightforward. However, if you were to build something like that with 74 logic, it's going to take up a lot of space if you really want to build a true memory mapper. Okay, so we need to construct a method of getting the data that we need, but at the same time we have to be cautious, because with CPLDs, unlike FPGAs, we have a fixed amount of flip-flops. For example, in the CPLD that I'm planning on using, we only have 128 macro cells, and each macro cell has 1 flip-flop. So for every flip-flop that we use, we are going to essentially lose an entire macro cell whenever we go to compile this. So that's another consideration that we have to take, is will our design fit into the logic device that we decide to use. So with that said, let's look at some of the requirements that we may need in order to build a system that can access up to 512 kilobytes of either ROM or RAM. So I'm going to get rid of this, and we are going to add in some inputs here. So if we imagine that we are going to divide the memory space up into 4 windows of 16K, we know that we are going to have, actually let's do it this way, we know that we're going to have to use the top 2 address bits in order to do that, because 2 to the second power is 4. There's 4 16K windows in a 64K system, so we know that we're going to have to use the top 2 address pins. Okay, and that complicates things because, actually, see here, that complicates things because we know that with a 512 kilobyte address space that we're going to need a few more address lines. We're going to need a total of 3 extra, and what I mean by 3 extra is that on a 512K SRAM, the highest address bit is going to be A18. So, knowing that, we know that that's the top. But something else that we haven't thought about is that we are going to need a few extras. It's not just the 3 that we need here, which is going to be A16, A17, and A18. We're also going to need to replace A4 and A5. So, or A14 and A15. So that tells us that we are going to need a system that gives us at least 5 bits on each latch. But more importantly, we also need to be able to distinguish between Rom and Ram. And the way that we would do that is having something along the lines of this, having a 6th bit that will tell us whether or not it's going to be Rom and Ram. And we only need 1 bit for this, and the reason for that being is pretty straightforward. Because 1 bit can give us 2 variables, either a 0 or a 1, that can tell us whether or not this is going to be a RAM address or a ROM address. So we need to come up with a way of taking 2 bits and turning it into 6 bits. Okay? And the easiest way of doing that is to have a octal latch of some type that we can actually take 6 data pins, latch the information from it, and send it over to these bits when that particular area of memory is enabled. So, knowing that, how do we construct it? Well, that's going to be the part that we're going to look at now. So, here we have a 5-bit address latch that I've devised. It's not too difficult to understand, but we're going to look at it just one piece at a time here. Now, obviously, we need 5 bits for the address plus a 5th bit for, 5 bits for the address and a 6th bit for the determination of whether it's going to be a ROM or a RAM address. Now, the way this circuit is comprised is it's pretty straightforward, and I'm going to go ahead and give you a theory of operation here. So we've got our 6 data pins here. We have our 6 outputs here. We have a clock pin, which is this CP, and if you go down and look, it's connected to the clock input of each one of these flip-flops. Now, we know that we need to be able to reset this to a known value when the system is reset, and each page would, if you didn't think about this ahead of time, each page would end up being set to the same area of memory. Now, this is pretty easy to overcome in software. You could, simply, the first thing that you do whenever you boot is to reset the page locations and then jump to next area of code. But we want a system to where we can actually determine how these are a memory mapper that is more universal. That way these things are going to start up in known states. So if I simulate this here, we're going to set this thing up so that it's essentially zeroed out. So think of this as the reset pin, okay? Clear, because that's what it's ultimately going to end up being. It's going to be tied to a reset pin. And if we clear out the system, we can tell that these pins are 0, and of course if they were a 1 they will be lit up. So knowing that these things are zeroed out, we know that we can clear this information out. And if we put data on the bus here and we clock the data in, we can latch that data. However, actually let's leave that on there. If we clear it, it zeroes it out. Okay. Now what if we decided that we wanted this thing to let's say that it's in the second 16K of memory in the memory map, the second window of memory, and we wanted to have this thing start up so that it's going to actually throw out an address that's the next 16K of, let's say, the ROM. So what we would need to do is we would need to essentially set this preset here, and of course this will be something as just a component of a larger system later, but we're going to tie this high. And the reason why we do that is because when we clear this, you'll notice the Q pin, Q0, the output, it's going to go high. And if I were to remove that preset and clear it, it clears just fine. We can do 15, it does the same thing, or we can do both of them and it does the same thing. When we go to reset the system, it's going to tie this high. And the way that it does this is it effectively takes the reset input and it ANDs it with the A14 or A15 input, and it one through a not input here, but the top one here, let's just take A14 as an example. It uses A14 and the clear input, and if that is, or if they are both positive, it raises the set line to a high, which goes ahead and sets this bit. Think of this as the preset, okay? And if the A14 is low and the reset line is active, then at that point it's going to clear this to 0. So that's how it works, and like I said, this is going to be one component. And the way that the memory preset works is essentially the same. So if we set this to high and we reset the system, this bit 6 is going to actually go high, and this is going to be used as a flag. And what I mean as a flag is in the larger block diagram of the memory mapper, this signal here is going to be used as a reference for the decoding logic to determine whether to activate the SRAM or the ROM. So if we set this to a 0, then we know that when we reset the system, or it's going to end up in ROM, or if we set it to 1, it's going to end up in RAM when it goes to access this. But the fantastic part about doing this way is that I can set this after the fact. Let's say that it's it's initialized as being a 0, so this area of memory would normally access the ROM. If I go ahead and set bit 5 high and have a couple bits here set to denote a particular address range, and I clock that data in, I've got my address range here, but I also have my my extra bit here for determining whether it's a RAM or ROM. So at this point it would access the SRAM at this page here. So now that we have an idea how to create a register that will access both RAM and ROM, we have essentially the start for a larger system here, a larger memory mapper. Now we're going to need 4 of these in total, because again we're using 4 windows, each of which can access a variety of different pages of memory. You could use this all the way up to 512K SRAM or ROM. So knowing that this is a single 16K window, we're going to need a total of 4 of these registers, and the construction of that is what we're going to be taking a look at next. So So I'm going to go ahead and put together a couple circuits here, and we will start the process of building up this memory mapper. Okay, so now we have our 4 registers. Each one of these is going to address a 16 kilobyte area of memory. Now I'm going to explain the organization of how I've got these set up. Obviously we have our 4 registers. We have our data pins or data signals for D0 through D5 connected to the inputs of each one of these registers. And then we have some ground and some power signals here. And the way I have this set up is so that, and we don't really need a 15 preset in this type of setup, but if you wanted to, say, address 48K of ROM or 48K of RAM, you would need that A15 pin. But in this particular way that we're addressing it, we don't need it in this circuit, but it's there in case we decide to change it at a later time. So on the first one, obviously this is the first 16K window. Now we know that we need to have the memory preset set to ground, and the reason for that being is because we're going to want to start off in ROM, and we're designating that bit to be a 0 for ROM and a 1 for RAM. Now on A14 and A15 presets, we also want to start off in the very bottom of the SRAM's memory range. So we are going to set both of those as low as well. Now on the second window, the memory preset's still going to be set to low because we're still planning on being in ROM, but we do need to set A14 high. And that's pretty common. You know, we want to be in the next page window, but we're leaving A15 pulled low because obviously we don't want to be in the third window or the third page. Now, whenever we get to this next 2 here, now we want to be in RAM because we want to start off with 32K of ROM and 32K of RAM. Not that we'll actually need that much, but it makes sense just to have the system well divided up. Again, you could set this up so that all 3 of these could be RAM, and then you could, you know, bank in whatever ROM you needed to after you do what you're going to do. It really is up to you. But we've got this one set up. Now we are tying that memory preset on both of these to high because we want to be in RAM. But we do want to be in the bottom page of RAM, so we are also setting A14 and A15 low. And the opposite here we're actually tying A14 high and A15 low because that's going to put us in the second page of the SRAM. Now the next thing that we have to take into consideration is how do we actually access these? How do we write data to them, and how do we manage this circuit here? And that's where we are going to go to I/O, because with I/O, if we put our registers in the I/O space instead of the address space, we're going to be able to create independent registers. Now I'm going to use addresses FF, FE, FD, and FC, very similar to what the MSX computers did. So we're going to use those top addresses for the I/O space, and we are going to create chip select signals so that we can write data to these when we are accessing that particular address for the I/O space. So I'm going to put together that circuit, and I will be right back. Okay, so now we have a little bit of I/O logic going on. Now what I've done is I've added in the I/O request, the write, the read, the A7 through A0 pins, as well as the reset pin. Obviously we need to be able to reset this to a known value, so we want the reset included. We're using the I/O space, so we do need to take into consideration I/O request, and we also need to make sure that we can write and read from these address registers. So that said, we need the write and read pin as well. And because we are working with the I/O space, we are going to want the addresses or address pins available to the system to be able to determine what these register values are, i.e. we're going to be using FC through FF in the I/O space. So we want all 8 of the address pins that are applicable to the I/O space. And what I've done here is, obviously the reset is connected up. It's pretty simple. You just connect it to the clear pin on the 5 address registers. But as far as the addressing is concerned, we need to do 2 things. We need to have the 4 chip selects for being able to latch the data into the registers, and we need 4 chip selects for being able to read the information from the registers. Now, at the moment, we're only going to be concerning ourselves with the writing of data, and what we have done is we have created a 8-bit OR gate. Now, this OR gate, if we zoom in here, it's got most of the pins are going to be knotted, the input pins, and the reason for that being is because we want a high on this. On address pins A7 through A2, we want those to be high, but we want to make sure that the IO request and the write pin on the first one is low. So if those 2 are low, but A7 through A2 are all high, that means that this here, the output of that first OR gate, is going to be low. Now, then we want to take the bits A0 and A1, and we want to put them through OR gates along with the output from this. And the purpose for that is we are creating active low chip selects. So if we set up 4 OR gates, the first one with all of them being standard, if all those pins are low, this output here is going to be low. On the next one, if A0 is high and the other 2 are low, we get a low here. The third, if A1 is high and the other 2 are low, obviously we get output. And if the initial OR gate output is low and the 2 last bits are high, then we'll get a low on the 4th one. And what that does is it gives us a clock pin that we can use. If you go over here and look at the first one, it comes right up, goes to our clock pin. And that allows us to latch that data into the system. And the reason why it's important that we have that is because we are wanting to store data here, and we need to write that in there. And we're using the IO request along with the write and the address in order to latch the data from the data bus. However, we are going to want to be able to read this data back as well. And in order to do that, we are going to have to use a second set of chip selects here, but utilizing the read pin. And of course it comes down here and it's factored into this second 8 input OR gate, and then the last 2 address bits are also factored into the 3 input OR gates. So it's the same scheme, we're going about it a slightly different way. The way that we have done this, obviously we have, I believe, 6 flip-flops within each one of these registers. So I guess it's about 24 macro cells that we've used, but I can assure you that with this small amount of logic, we're not going to have any higher of a utilization within the CPLD than what we currently have with just the flip-flops. So this allows us to utilize up a lot of that logic that's already built into those macro cells that we've already used just by consuming those flip-flops. And because of that, now we're able to both write data in, and soon we will be able to read that data from the register as well. Okay, so now we're going to construct a circuit that's going to allow us to actually read the data from these address bits here. And that's going to help us out a lot because, like I said before, we are going to want to make sure that we can read this data for purposes of reference. So in case we are trying to remember which area of memory we were addressing within the computer software, we can read that register, find out what it is, store that value either in a internal register to the CPU or in another place in memory, and then refer back to it at a later time. So we're going to go ahead and start constructing that second order of inputs here, and we are going to expand this system piece by piece. So now we've reached that point of exponential growth. So Now we've expanded upon the circuit to include the ability to read and write the data to the bus. Now, in reality, if you were doing this from, discrete logic, a lot of this you wouldn't need, because it's going to have output enables and simply tying in to the, for example, a driver chip transceiver such as a 74 HC245 or something along those lines. You would be able to read the data from that port and not have to worry about a lot of this logic. But we are focusing on designing things digitally for use in CPLDs, so we've got to include some additional logic here. So these chips right here are all identical, and we're going to take a look at them real quick. So if we open this up, it's pretty simple. It's a driver chip. Now, you have to remember, when you're using digital circuits, a lot of things that you would normally use, such as tri-stated drivers and things like that, you're not going to use until you get to your top level design. So you have to come up with other ways of being able to create drivers, so to speak. And this is one that I created here. This is a 6-bit driver. Essentially, the way it works is if the input is high and the enable pin is low, it's going to gate this AND gate to turn this bit on. So if we simulate this, if the enable goes low, that bit goes high. Otherwise, I can turn on any of these I want to. They're not going to turn on at all. But if I hit that enable bit, all of a sudden we get the outputs. And that's essentially what we're doing here. And I have essentially a whole bunch of these drivers here. And the reason why is we need 2 per register. Now, the first one, it's going to be used to create the address signals for the computer. And I've got these labeled as A14 expansion through A18 expansion. And that's just to show that there's a difference between them and the normal address pins that you would have over here. Now, the 5th bit I don't actually have connected at the moment, and the reason for that being is because we are going to use that along with some additional logic to create essentially chip select signals for whether it be RAM or ROM. But our first driver chip here, its whole purpose is to basically its whole purpose is to create this a multiplexed address bus here. Essentially, each one of the pins from this, it goes through an OR gate. So in other words, Q4, 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 and Q4 all go through this top OR gate here. And if either one of them is high, then A18 is going to be high. And the reason why you have to do it this way is because in this software package you cannot connect these outputs together. So even though they would only go high in the event that that particular chip is selected, it's not going to work that way in digital logic. And the reason is because this is going to be high or low. If one is high and the other is low, it's going to be sinking current, which is going to essentially destroy the internals. So you have to pass them through an OR gate like this. And then the second set of chips here, these are the second set of drivers rather. These are being used to essentially do the same thing, but for a data output. Now, again, if you were using regular, discrete logic chips, you would be able to, put these all through a, transceiver, and you'd be able to tell it whether you were sending data or receiving data. But in this particular situation, we have to do it this way, just simply due to the differences between designing digitally and designing something for a board layout. But the function that we have here is essentially we've got our chip selects from previously hooked up to the address registers, and of course if we write a value to a given address, it's going to latch that data in. Now the second set of drivers here, these are so that we can latch or the second set of chip select signals, that is, those are there so that we can actually read the data on the drivers here and output the data to the data out port. And again, we have data in and data out. Now, the third thing that we have to do is make sure that we take those chip select signals, we pass them through another OR gate that is knotted on the inputs, so that if either one of those is a low, then it's going to produce a high, and that's going to be our data out enable bit. And that's going to, and of course, once we compile this, that's going to be incorporated into a larger system, and this is the pin that would or the line, the signal, if you will, that would essentially tell the rest of the system, okay, I'm reading data now, so take data from this. So if you imagine this is all single little chips, such as this register chip here, imagine all this is inside one of those blocks. When we would hook something up to this, we would essentially put tri-state buffers on these, and we would use this signal here to gate those signals so that they are only being sent outwards in the event that this is a high. And that's kind of the purpose for that. But we still have some more work to do. Now what we need to do is we need to actually use these signals here to create a Ram-Rom signal. And we also need to create some logic for determining which one of these chips is going to display its data onto the address bus, because we haven't come up with that yet. So we'll take a look at that next, and in the meantime, you might want to start thinking about the exponential growth, because as you add more things, you have to add more things. So your schematic is going to grow like this, and it is very easy to get lost. So bear that in mind. Now, like I said, we're going to take a look at creating some of those select signals next. So we'll get right at it. Okay, so we are back with our new logic that we've added up here to not only gate which window we're trying to see the contents of on the address bus, but also whether the contents are going to be gated to the ROM or the RAM chip. So let's take a look at the memory banking scheme that we're using first, or the memory decoding scheme. So this is pretty straightforward. We're using A15 and A14 in order to come up with 4 chip selects. A15, if it's low, and A14 is low, this first chip select is going to also be low, which is going to drive the enable line low. And that's important because we've designed this to be an active low rather than an active high. I'll scroll over so that you can see that. But it does come through here. It goes to this enable bit right there. Now, if we look at the second one, it gates A14 as high. Essentially, if A14 is high, it's going to be a not bit there. So it's going to drive this low, which is going to go down to the second enable bit, so on and so forth until we get to the last driver here for the address bus. Now, the chip select, it's a little bit different. So obviously we're using the memory request signal here to help gate this along, but essentially we're taking the 5th bit of that address register or page register, whatever you want to call it, and we're sending it through 2 OR gates. Now, the first OR gate, it's 5 bits, and it essentially takes all 4 of the bits from the 4 address registers along with the memory request bit. If any of them are high, the chip select for the ROM is not going to be active, it'll be inactive. because we know that memory request has to be low in order for it to be a valid memory request. We also know that we've set or designated that bit to be low for ROM or a 1 for RAM. So if any of them are high, the chip select for the ROM is not going to go active. However, on the second set that we have here, we obviously want to make sure that at least one of these is high, and we NOT it on the output of that OR gate, which this is actually a NOR gate, if you will. But we NOT it. So if one of those is high, the output here goes low. If memory request is also low, then that means that the chip select for the RAM is going to go low. So that is pretty self-explanatory. And really, that's about it for the memory mapper. I don't think that there's anything else that we really need here in order to make this functional. The next thing that we need to do is to run this through the simulation and make sure that it's going to work properly. So we're going to do that next, and I'm going to show you some of the features of this and why this design, in my opinion, is a very good design. Okay, we have this booted up in the simulation now, and you can tell because I've got some of the inputs here highlighted, and you can see some of the outputs here highlighted as well. First thing we're going to do is go ahead and reset the system so we know it's in a fresh state. And we're going to take a look at some of the features that we built into this. So the first thing of note is when we design these registers, we designed them so that they could be preset upon startup. And of course, if we reset the system and we are looking at, for example, the very bottom window in memory, we can see that as we wanted, this actually is A14, A15, 16, 17, 18. They are all at state of 0. Now, if we simply go to the next bank here, we can see A14 lights up. And we know that we reset this, so that's kind of a no-brainer. It starts up. We go to A15, again, 0. So the idea being is that the first two windows are going to start up in ROM. The second two windows are going to start up in RAM. And they're going to start up at the bottom 2 pages of each. So if we go to A15, like I said, it starts up at 0. And if we add A14, it again lights up A14 on the expansion address pins. So that shows that it's working. So, of course, if we want to actually see the contents of that, let's say that we go to A14 there, and we select memory request, the chip select for the ROM goes low. And if we turn A15 on, the chip select for the RAM goes low. And of course, we could remove A14 and the RAM chip select stays low, but A14 disappears. So that's good. That's exactly what we wanted. Now, the next thing that we need to do is take a look at the I/O and the registers as a whole. So if we go in here and take a look at the controls for the I/O here, let's say that in this very first register we want to write the value of let's say 1, 3. So 1 and 3. So I/O request goes low, we write it, and when we raise this bit, you'll see it lights up right here. There you go. Now, we wrote that to the very bottom register, so if we actually put that A15 and A14 low, we can see that we have 3 on the, I'll say that's 3. Is that 1, 3? No, I'm sorry. That's actually 2, 3 on the data bus. So we can see that we have 3 right here. And if we actually take into consideration this top bit, that's a 1. That means that when we go to cycle this on the memory request, we should get RAM instead of ROM. So as you can see, the RAM chip select goes low. And if we reset this, it'll flip this bit up to the ROM chip select, and then it'll zero these out. And I can prove that just by doing this. There we go. So the next thing that we want to look at is the ability to read from these registers. And of course, we write that data bit again. Of course, you'll see those lines slide up. There you go. Now if we come down here and take a look, if we actually read from this, and of course let's zero this out so you can see there's no tomfoolery here. If we write the read signal low, we now get that data on the output port, and what we get is 2, 3. So that's a top bit right there, bit 5. And bit 0 is down here. And then we have our D out signal here. And the D out enable, again, that's used externally to help gate this tri-stated on the outside of the diagram. So if we raise the read select, all those go back to 0, and we still have that data up here, as you can see. So that's the essential operation of it. You can write to all the registers. So let's say we want to write to the next register. Let's say we want to write all of these. Let's go ahead and write that. And then let's say just 1 bit there. Write that. And then for the last one, let's just that top bit there. So we've written all those bits, and if we go to check these with the address pins up here, you'll see the bottom window, A14 to A15. Go to the next, we got 1F. Go to the next one, we've got 3, and if we go to the very top window, we also have 3. So that's the way that it works. So it's very versatile. You can, write these pages to the registers, and then if you need to, you can read that data back and, for example, store it in another register internal to the CPU or in another place in memory. However you're going to store that, so that you know which page you're supposed to go back to, and then flip in a different page, either read or write information, do whatever you need to do in that second page, and then flip back once you're done. So it's very handy for being able to keep this data there. And of course, you could expand this. Let's say that you wanted to add another register that you could read one of these values in, store that value back into another register for safekeeping, almost like the alternate registers on the Z80. And then, once you're done, flip back to the original. I mean, you can expand upon this as much as you'd like. It all comes down to what size device that you're planning on using. But this is not very big. Like I said, I think that there's 24 flip-flops here, which means that we're going to use at least 24 macro cells. But the rest of this, to be honest with you, I think would probably fit in the macro cells that we've used. I don't think that we're going to use up all of the discrete logic within those macro cells. So I think that this would be a very safe bet whenever it comes to expanding. And of course, I'll provide a PDF of the schematic on my website. That way you can download that. Of course, I'll put a link to it down below. But yeah, no, this is a good little memory mapper in my opinion. I don't see anything wrong with it. I think that it would work out very well. If you have any questions about it, you're welcome to ask those below, or you can go to the website and send me an email. But yeah, no, this is what you have to take into consideration when you're designing a memory mapper. You know, some people will just use a single octal latch, and they will use that. And you know what? That's fantastic. If that's the way that you want to do your memory mapping, that's fine. But it's kind of basic, and something like this gives you a lot more capability, and it greatly expands your memory map so that you can do many, many more things than what you would normally be able to do with memory. So I hope that you enjoyed the video. If you have any questions about it, like I said, feel free to ask them below. I'm going to also post a short little write-up about this on my website, and I will put a link to that. It'll contain the, like I said, the schematic and PDF form for this, because there's so many self-made little circuits here that are included in this. I'm not going to upload the file itself, because you would have to have these in order to really make it any use, and you're starting to go down the rabbit hole there with this type of stuff that I would have to include. So it's going to be easier just to provide the schematic, and I'll provide the schematic for the individual ones as well, these little embedded circuits, if you will. But yeah, that's it. So if you have any questions, like I said, ask them below. Other than that, I hope you enjoyed the video, and have a great day. See you next time.